Again, I'm Brian Teitelbaum. I'm one of the applications engineers here at AEE Solar. And today we're going to talk about using wind power in off-grid power systems. So this is going to be only a primer. We only have an hour, so I can't go into a whole lot of depth, but hopefully I'll cover things, and then I'd be happy to answer any questions as we go along and at the end of the presentation. So let's in here, and you might have to choose my voice a little smoky here in Northern California due to some wildfires, and playing havoc with my sinuses, but hopefully we'll get through this. Okay. So let's see here if we can get in here. First I want to talk about why small wind turbines are more useful in off-grid setups than in on-grid or grid-tie systems. And it's primarily because off-grid systems need to be able to produce energy on a daily and weekly basis instead of on only a yearly basis as you get with net metering and grid-tie systems. With grid-tie systems, it doesn't really matter when you produce your energy over the course of the year. It could all be in the daytime. It could all be in the summer. You bank that energy as credit on your utility bill. You can use it in the wintertime. In an off-grid setup, we don't have that yearly basis. It's not really practical or possible to have a battery or a storage system large enough to store energy from the summer to use again in the wintertime. So systems really on a constant basis, daily and weekly, and therefore wind power could be really useful for doing that. So with grid-tie systems with net metering, since it can do a yearly accounting, really PV power is the most cost-effective way to do that, especially with the lower cost of PV these days. Adding wind systems to grid-tie systems, unless you're in a very windy location, is not going to be very cost-effective. However, for off-grid, since you need to produce energy even in the darkest months of the year, off-grid systems can greatly benefit from having multiple energy sources. The sun's not always shining, so and very often when the sun's not shining, the wind is blowing. So it's a way of being able to produce energy, for a longer period of time in a day, or for more consistent production over the course of time, particularly in the wintertime. And since energy storage is limited by battery capacity, we really do need to be able to produce energy when we can get it in systems. A great addition to many off-grid systems. Solar is used for all off-grid systems, or virtually all off-grid systems, and it's a critical component. But solar does have lower output during the winter months and diminished output during inclement weather. If it's cloudy or stormy, you're not getting a whole lot of solar power produced. And obviously solar has no output at night. Whereas wind power is generally most effective during the winter when solar is more limited. Average wind speeds is usually highest during the winter months. Air density is greater during the winter months, and we'll talk about air density and its effect on wind power in a little while. Wind on average is stronger during inclement weather. It might be very stormy out, you're not getting a whole lot of sun, but usually the wind is blowing at that point. And wind can blow at night, and very often during winter nights. Of course, that all depends on your local climate and where you are. But it's a way of producing energy during times when you're not getting sun. And here's kind of a good graphic that kind of shows that, based on a kind of a sun chart, but it also shows that very often wind has its peak in the wintertime when solar has its low point in the wintertime, and can be an excellent complement to a solar power system. And I might also add that hydroelectric will do a similar thing if you have a resource for small hydro. Very often that runs more in the wintertime than the summertime, and it's also a constant production of power. It's just another way to spin a turbine, essentially. We'll talk about mostly wind in this presentation. Here's a few examples showing both sun chart and wind chart for the year in various locations. Now, all of these are fairly windy locations, but you can still see from the chart that solar peaking in the summer and being low in January and December at the two ends of the blue lines, whereas those are the times where wind is the highest during those periods of times. So they make an excellent complement for each other. And And one of the big advantages of having some sort of constant charging is that not only are you producing energy, but you're also reducing the discharge on the batteries. So you don't have to catch up as much after a storm as you would with just a plain PV-based system. So what is wind? Well, wind is air, and air is a fluid like water and has similar characteristics. I know this is fairly confusing to some people because very often the word fluid and liquid are intermixed, but they're really two different things. Air does act as a fluid. It has the same characteristics in fluid dynamics that water does. It's just a much thinner fluid than water is, but actually it acts the same way with eddies and currents and backwash is the same thing that a stream would do. Air, while less dense than water, is still a relatively dense material. This is obviously true if you come in from outer space and you hit that air, it's going to be pretty darn dense. And as you can see from our meteor shower that we just recently had, when things enter from space, air. So wind is air in motion. And the air motion is caused by differentials between warm and cool air masses, which create areas of higher and lower air pressure. And those air masses are warmed by solar energy. And the thing is, the solar energy warms the Earth's surface and warms the air masses in unequal amounts over the surface of the Earth. And that's how we get the differentials between warm and cool air masses. So in a sense, wind power is a form of indirect solar power. And you can see from this little picture here of an airplane wing in a smoke chamber that, it really looks like water, even though that's air movement that you can see. It really has the same kind of effects. So how do wind turbines work? Well, turbines convert the kinetic energy in wind into mechanical energy, a spinning rotor generally, and that's connected to a generator, which turns it into electrical power. Power production is affected by the wind speed, the density of the air, and what we call the swept rotor area of the turbine. And,
hey Brian, we're getting some really crazy whistling sounds coming from your audio occasionally. Do you know what that could be, or do you want to try calling back in?
No, I really don't. It's clear on my end. I apologize for that, folks. I am calling in from an off-grid location with a wireless internet link. Sometimes it has some strange things. It usually works pretty well. Is that better, Hannah?
It sounds okay now.
Oh, interesting. Must have been a sunspot or something. Anyway, I apologize for that. Hopefully my presentation will be understandable. But, if I need to repeat something, please write in. I'd be glad to go over something again. So as I was saying, the swept area of the blades is the area of the wind or the air movement that is being captured. The energy in that air is being captured over the swept area that the rotor is able to spin. The energy captured by the rotor is linear. So if you double the swept area, and that's area, not just the diameter of the rotor, but the area of the rotor, the amount of energy it can capture is doubled. However, potential wind power increases with the cube of the wind speed. So if you double the wind speed, you actually get 8 times as much wind power. And this is really an important point. You may see a lot of advertising for wind turbines that advertise, a starting speed at 3 or 4 miles an hour, for instance, and it'll start producing energy. Well, that may be true, but there's not a whole lot of energy to be captured in a 3 or 4 mile an hour wind. You really do need a good wind, generally over 10 miles an hour, before you have any substantial power to be able to capture with any kind of wind turbine. So there are several varieties of wind turbines that are out there. We're going to talk mostly about horizontal axis wind turbines, or HAWTs. This diagram is showing a Savonius turbine on the left and an Aeris turbine on the right, vertical axis wind turbines. There are many designs of all of these on the market. However, the vertical axis wind turbines are really not nearly as efficient as a horizontal axis turbine. There's a really good reason why big wind turbines in big wind farms use horizontal axis turbines, and it has to do a lot with just the physics of being able to capture energy, being able to get them up higher on a tower without stresses on the tower that you get with a vertical axis turbine. So I have not seen any designs of any vertical axis turbines that really are exciting or really produce any power for the amount of investment you put in them. And I would actually advise people pretty much to stay away from them. They do make nice kinetic art, but if you really want to produce energy, you really have to go with a horizontal axis turbine. So here's some winter factors I want to go through. Air density versus air temperature. The air gets colder, and the chart gets colder on the left in degrees Celsius. The density of the air goes up. As the air cools, it becomes more dense. As it warms, it becomes less dense. Obviously, the denser the material that's blowing through, the more power is potential in there. So this is another reason why wind turbines tend to work better in colder conditions or in winter conditions than in summer conditions. There's also an elevation factor. Air density is reduced at elevations. So obviously thinner air, again, contains less energy. So like you can see here on this chart, for instance, at about 8,000 feet elevation, there's only 75% of the air density compared to sea level, which means that you only can get 75% of the potential energy out of a certain size wind turbine as you would at sea level. So this is a big effect, especially in the Mountain West, that you have to calculate for that and be aware that elevation is going to affect the amount of energy that you can get. So in terms of siting wind turbine, there are good sites and there are bad sites. And determining where those sites are on a particular property is going to be important because a turbine placed in a poor wind site is going to perform poorly, obviously. There are a number of ways to determine that. This chart in the upper left here is called the Griggs Putnam Index, and it's a way of looking at trees and vegetation on the property or in the area, and you can tell a lot from how they grow as to what the wind regimens are in those areas. You know, obviously if you have trees that are what we call flagged, where they essentially all grow in one direction or they're even leaning over, like you see on many sea coasts, those are very windy areas. Places where trees grow in perfectly symmetrical vertical forms are probably not very good areas for wind power. There's also turbulence issues with trees and buildings and other kind of obstructions to the wind. We need to get the wind generators either away from those obstructions or much higher than the obstructions. Go through a little more detail. And the type of land form can also have a big effect. For instance, at coastal or lakeside, you might actually get a wind effect off the water. That can be an upswell when it hits land. That can actually be an excellent place to gather wind power. Tops of hills where the air and the wind are compressed as it blows over the landscape can actually increase the amount of wind and increase the amount of power production. Plateaus and mesas can also be good, although if you're too close to the edge, you're going to get a lot of turbulence there, so that's not necessarily the best place to be. So there's several things to consider when you're doing that. In general, and this is a general rule of thumb, the lower blade tip of the turbine should be at least 30 feet higher than any buildings, trees, or other obstacles within a 300-foot radius. Those numbers change depending on who you talk to. Some people say 20 feet higher in a 200-foot radius. Some say 50 feet higher in a 500-foot radius. Actually, this chart on the page is really accurate looking at it, and it really depends more on the height of the obstruction. And that if you look at this diagram, you can see the building is what we call H, that's the height of the building, and really in front of it from the prevailing wind side, you need to be at least 2 times the height, and on the trailing side of the wind, 20 times the height. And near it, it needs to be twice the height. So you can see this effect very easily with things like a weather balloon or a kite with streamers attached to the string at 10-foot intervals, and like it shows in the diagram, in places where there's a lot of turbulence in the air, those streamers will be blocked around and not really be in a straight line. It's not till you get up into the laminar flow of air beyond the obstructions, beyond the turbulence created by the obstructions, that you get a smooth flow of air. And it's really that smooth point is really where you can grab the most wind power. It doesn't necessarily mean you can't get any power at a lower point, but the power will be reduced. It's going to cause wear and tear on the turbine, few other things. So really, ideally, if you're really looking at getting power from the wind, you really need to be up in that smooth air, and that generally requires very tall towers or towers that are far away from any obstructions. So, you know, it's putting a wind turbine on a short tower is like putting a solar array in the shade. You're just not putting it in a place where you can grab power. And this kind of gets back to the idea of air being a fluid. I mean, essentially, we're like creatures living on the ocean floor of this ocean of air. And as this ocean of air, the current of this ocean of air moves over the landscape, it's rubbing against the ground, it's bumping up against trees and buildings and hills and whatnot, and all those things create friction, which rob the energy out of the air. So if you really want to get power, you need to really get up into that flow, into that current of air that's higher up off the ground. A number of ways to do that. There's a number of different tower designs that are available. The tilt-up tower design is the easiest to set up. It's the easiest to service. It doesn't require any climbing. You can raise and lower the whole assembly down to the ground, do all the assembly and all the maintenance on the ground, and then raise it back up. It's a very convenient way to do it. They're somewhat limited in height to do that, just the stresses of raising and lowering. There are other types of tower, guide lattice towers and freestanding towers, monopole towers that are all available for different purposes and work, you know, better in different sites. Obviously, the lattice and the pole towers, the self-standing lattice and pole towers, don't have guy wires, so they take up less space, but they do require a crane to set up, so you have to be prepared to be able to do that. The guide towers, at least tilt-up type, can be set up with just a winch or a truck winch or even a four-wheeler. I've used that before to pull up wind towers. Fairly easy to do. The critical to get in the geometry, but other than that, it's a fairly simple way to do it, especially easy on flat ground. So as wind speed increases with tower height, again, if we're getting off the surface of the Earth itself, you get stronger winds. Higher towers also raise the turbines above the turbulence that can exist close to the ground. So, you know, you see in this diagram here, you know, at the bottom end is a 33-foot tower, and the wind speed in this particular example is 12 miles an hour. At that same location, at 90 feet, the wind speed is 75% more than that, and you get 13.5 miles an hour. So as you go up in height, you're getting more wind speed, and obviously you're going to be able to generate more electricity at that point. So you do need to ensure there's enough room at the site to raise the tower. Generally, the tower needs to lay down and be assembled, and then is lifted into place either with a crane or with guy wire. Most areas are super towers that typically in rural settings typically requires that the tower be at least 1.5 times tower height away from the property line. Obviously, you'd have to check with your local codes and your local building department and whatever restrictions they may have for the area. This generally precludes using them in suburban areas. It's really more of a rural type of thing, but that's usually where the off-grid systems are, so that's generally not a problem. We don't recommend mounting wind turbines on roofs of buildings for several reasons. First of all, that's not a very good wind site. The building itself is creating a lot of turbulence, so you're going to get a lot of turbulence from the wind there. It's not a great place to produce power. But also, anything that spins, even if it's perfectly balanced, is going to create harmonic vibrations. And those vibrations can be amplified building in the same way that sound is amplified in the body of a musical instrument like a guitar. And so not only in general is going to amplify that noise. So it's really not a good idea to attach wind turbines to buildings. If they're a concrete structure, that may be okay, but it's still not really a good idea. I've also seen wood structure buildings damaged by wind turbines that are mounted on them due to the vibration. I've seen like nails worked out of rafters and that kind of thing. So really not a good idea to attach a wind turbine to a house. So in determining the wind resources in the U.S., the National Renewable Energy Lab does have a whole lot of data that they've gathered from a period from 1961 to 1990 at 239 locations around the U.S. This could be very helpful if you're near one of those locations in determining what your wind potential is at that site. And they also produce things like this map. Now, this is a wind map of wind potential in the United States. And you can see, for instance, that places, a lot of places in the southeast and have a lot of wind resource even in the wintertime. Those areas are probably not a good place to add wind. I mean, you may get some power out of them, but it's probably not going to be a very return on investment in those places. But other places with the darker blues or the black areas are very windy in the wintertime, and wind power can be a very excellent source of energy. So how do you integrate a wind turbine into an off-grid power system? Well, it depends on the turbine. There's lots of different designs out there. Some turbines have direct DC output, generally at battery voltage, so the turbine is chosen depending on what voltage the battery system is, usually 12, 24, or 48 volts DC. There are some higher voltage systems, generally used more for industrial applications, but generally what we deal with is up to 48 volts DC. Generally, these units have built-in battery charge controllers, so no other equipment is really required for them. They can just be hooked right into the system. However, because of low voltage, it is more difficult to run power for longer distances. So if the tower needs to be really far away from the power system, you have to use some pretty big wire to move that power in there, even with small turbines. And then there are many turbines that just produce a three-phase AC output. Now, it's a wild voltage and frequency output, usually three-wire. It's not generally usable directly because the wind blows at variable speeds, so the turbine is spinning at variable speeds, which means you're going to get a huge variation in frequency and voltage going on from there. So it's not like you can have a three-phase wind turbine run a three-phase load directly. That's really not going to work out. What those are done is they're typically rectified to DC for battery charging, or rectified to DC for going through a grid tie inverter is another potential, but it still needs to be brought down to the current, which will be more constant. The voltage will be more stabilized. This frequency is at point. So typically they do require external charge regulation, which means a diversion controller such as the Morningstar TriStar pictured here, and a load such as this DC heater load pictured here. You could also use an AC dump load if you have a relay that turns an AC load on run by the inverter. In some way you need to be able to dump or divert that energy once the battery is full. You can't just disconnect the wind turbine in the same way that you would disconnect a PV array. A PV array there's no moving parts. You can connect it or disconnect it. There's no damage to the PV. When you're dealing with a spinning turbine, however, you don't want to unload it. If you disconnect it from the battery, it's going to be freewheeling. It's probably going to overspeed, and it could cause damage to the turbine, and it could be a dangerous situation. So the turbine has to remain loaded when the wind is blowing. So we use diversion loads essentially. So for instance, if you have 500 watts coming in from a wind turbine, battery is full, actually control a 500 watt load, and the turbine would still produce 500 watts, but it would just be burned off by the heater load. We also have water heating elements. You could heat water with it. You could pump water with it. Anything that you can use that consumes energy at that point it can be used as long as you're not putting more energy into the battery, thereby overcharging it or disconnecting the turbine and overspeeding it. Most of the three-phase turbines do come with a preset rectifier controller package as part of the turbine package. So very often you don't have to add these kind of separate components, but we do offer the separate components if you need them. And you connect it to the power system through a DC circuit breaker, the same way you would a solar charge controller, essentially. It's acting a little differently in this case. The wind is coming in through a circuit breaker to the battery. Another circuit breaker has output to the diversion controller and the heater load. The heater load is still connected to the wind turbine. So that's one strategy to do that. But you have to remember and have a place for a DC circuit breaker input into your power system. Midnight Solar's come out with a really interesting set of products that is a completely integrated turbine control, and not only for wind, but also small hydro. They have a clipper, what they call a clipper, which works with their classic charge controllers. And the clipper communicates with the charge controller and can actually slow the turbine down when the batteries are full. The clipper does contain heating elements in it and some electronics that can, exactly match the heater load to the output of the wind turbine, and that's all controlled by the classic charge controller. So it finds essentially a MPPT point for the wind turbine and can operate that turbine at its highest efficiency, and also can actually slow it down in high wind situations or in situations when the batteries are full. It has a maximum open circuit voltage limit circuit, which protects not only the turbine, but all the electronics in the system, and it keeps the voltage from spiking during high wind situations. Excellent controller for that. It does sense the incoming voltage from the turbine, uses the internal loads to hold down the voltage point. And there are AC and DC models from 1500 watts to 4000 watts. The AC models have built-in rectification to rectify it to DC. And there's a bunch of different models with different resistance values available. So depending on the turbine, and we need to get the specifications of the turbine in order to size the system correctly. But Midnight Solar will work with you on that to get the exact match on that, and you can also work with us to figure out the best components for that situation. But a very excellent system for wind power. So I'm going to talk a little bit about Primus wind turbines. At this moment, the air wind turbine, we have there are other wind turbine manufacturers out there. Most of them sell direct, so you can purchase directly from them. They don't go through distribution companies such as AEE Solar. So you can pick up the turbine from another manufacturer. We can supply all the rest of the balance of systems, the controllers and wiring and all that kind of stuff. So I'm doing this as kind of a general point on wind turbines, but really at this point we only carry the Primus wind energy turbines. There is another major manufacturer that is rumored to be coming out with their own wind turbine here shortly, and we'll probably be carrying that and hope to expand it in the future. But I have to say that the small wind market has shrunk quite a bit in the past 5 or 10 years, primarily due to the fact that photovoltaic prices have dropped so much. It's become a situation where PV was very expensive, so wind was very cost effective in a lot of systems. Now, because PV has so inexpensive, wind power has become less useful out there. But as I explained earlier, it still can be very useful in hybrid systems. So there's a number of different models of the air wind turbines. The Air Breeze and the Air 40 are really the ones that are designed primarily for like off-grid homes or recreational vehicles or use on land. The Air X Marines and the Air 30s are really more for high wind areas and industrial applications. They're all rated similarly, although the Air 30 and the Air X Marine do have higher peak outputs because they can handle higher wind speeds. However, the Air Breeze and the Air 40 are much, much quieter. So really for most residential situations, it's going to be an air 40, and you have an air breeze, which is more sealed for coastal and corrosive applications if you're at a seacoast. So one of the we're able to make these differences in blades. The air 40 and the air breeze has 30% more surface area than the air 30 blades, so it can achieve a lower startup speed at lower wind speeds and operate at lower RPMs, which makes them quieter. However, they can't produce as much power in high wind. They have to kind of protect themselves there. So the air 30 really requires a higher wind speed to start up and operates better at much higher wind speeds and much higher RPMs. But they also are a lot noisier. So, really if noise is an issue, if it's near a residence or in a residential area, the air breeze or the air 40 are really going to the ones to choose there. And here is showing power curve difference between the two. The air 40 air breeze is the red line there. So it doesn't have as much of a peak as you can see the blue line has, but it actually has a more consistent production. Let's turn that off here. Has a more consistent production through the that the Earth does, which has a higher peak and operates at actually lower output at high wind speeds. But the air 40 and air breeze are actually going to be cutting out at speeds about 40 miles an hour or above, whereas the air 30 and the air X Marine will still be producing power at that point. So this is another type of graph showing monthly energy production. And again, it's the orange line here, that's the air 40 and the air breeze, and it's showing a higher production of kilowatt hours over a month. The average monthly wind speed is at the bottom of the chart. The air 30 and the air X Marine have a little less monthly output, but again work better in much higher wind regimens. And that's really where. So in terms of noise, some studies have been done on these in terms of mapping sound data. And in general, the turbine sound blends into the background noises at most winds, really higher wind speed, loud, and of course the sound of the wind is pretty loud at that point. And most people are not really outside when you get into 30, 35, 40 mile an hour wind speed. So not generally a problem. So really, these are very quiet wind turbines. Obviously, there's going to be some sound. Anything that's spinning, moving through the air is going to produce some sound. So be aware of that. They're not as quiet as PV, but of course that sound means you're producing energy. So it's usually a happy sound for most homeowners. This is another way of showing the wind regimen here. This is a location of Cheyenne, Wyoming, rather windy spot. The upper left, you can see the average monthly wind speeds are pretty high. In January, you're approaching 16 miles per hour, which is a pretty strong average wind. Again, that's average. It's not just instantaneous. And in the summertime, it goes down, but you're still above 10. It's a pretty windy site. It's also you can see sun and then the two bottom charts are showing amp hours produced per day and also kilowatt hours per day. Sorry about that. And you can see the difference in the amp hours per day, for instance, it's showing a difference between a 12, 24 volt machine. Obviously, the amp hours are doubled at 12 volts than they would be at 24 volts, but it's the same amount of energy produced, which is the kilowatt hours per day shown in the lower right chart. So here's a few pictures of wind turbines. This is near a house. It appears to be very close to the house, but I think that's just an effect of the photography. But certainly used in an off-grid house situation, and that is a guide tilt-up tower that you're seeing there. Primus Wind Power has a unit that's 45 foot. It makes a nice wind tower for areas that don't have tall trees or very tall buildings nearby. Here's a little more remote location, somewhere in either or somewhere in the Asian area. And that's a fairly short tower, but as you can see from the landscape, there's not a whole lot of obstruction there, so it probably still produces a lot of power. Marine applications are an excellent place. Again, this is a short tower, but the wind going over the water is really not obstructed by much, and you can actually produce quite a bit of power on a boat of this type here. Here's some examples of using them in either data monitoring or weather stations, or in water pumping applications, controlling valves and whatnot. Again, it's combined with photovoltaics to provide a more reliable energy system for charging batteries and running equipment. This is a science weather station and research station down near the South Pole. You can see by the way they mounted the PV modules just vertical on the wall that being that far south, really a 90-degree mounting works out very well, and very cold air and a bleak landscape. So they've put up 4 of the turbines and produce a whole lot of power there. Another example of a research station in Antarctica. You can see the wind turbine is spinning, and the PV module is actually covered with ice and probably not producing a whole lot at that point. Telecom applications, very common, and this is a place more likely to have an Air 30 or an Air X Marine. Noise is not going to be an issue here, and being that high up and very often on mountaintops, it's going to be a very windy location. I believe this one is someplace in Africa, if I'm not mistaken. Again, offshore places, this is a Coast Guard buoy, a navigational buoy, and weather station. Again, a great place to have wind power to add to the solar and be able to have a more reliable system as a hybrid. Train and traffic signaling is another place. Again, these are often remote locations. Systems, switchgear and monitoring systems run off batteries, and TV will make it much more reliable where there's no access to any other power sources. And then just for fun sometimes. I often, maybe not so much anymore, but have gotten questions in the past about mounting wind turbines on your truck or your car or your RV and being able to produce energy as you drive down the road. Yes, you will produce energy, but the drag from the wind turbine will burn up more gasoline in the vehicle than the energy is worth. So there's really no gain there. I don't recommend that. I don't think it would be approved by the highway department. Very likely be pulled over by CHP or highway patrol or something like that. But in a stationary application, you could set up a wind turbine, especially if you're going to be there for a while, and gather quite a bit of energy. So at this point, we have a bit of time for questions. I'd be glad to answer any questions that come through.
Great, thanks so much, Brian. We do have a couple of really good questions, and just a reminder to everyone that you can submit your questions through that questions pane on the right-hand side of your screen. Just keep them coming. And also, just as a quick reminder that that survey will pop up once you leave the webinar. And if you complete the questions, it's real quick, I think only 5 really quick questions. I will send you a copy of this presentation. All right, so let's kick it off. Brian, our first question we have, is there an effective blade coating for preventing ice buildup?
That is a good question. Well, there are. I mean, the materials in the blades vary. Some blades are just plastic, some are made out of carbon fiber, some older machines just use wood. Sitka was an excellent wood to use for wind turbine blades. And very often, the wood ones in particular were varnished and then waxed. There's a couple of things here. Not only do you want to prevent ice buildup, you also want to prevent, bug debris buildup, and you also want to just make the blades as slippery as possible through the air. Obviously, if it's friction in the air, slow down, the more slippery the surface you're going to be. I don't know of any specific coatings that aren't done right from the factory by the wind turbine manufacturers. I would just say a paste wax would be an excellent thing to put on just about any of the materials to help do that. And yes, icing up can be an issue in freezing rain situations. There may be times where you actually want to shut down your wind turbine and wait for better weather. One thing I did discuss in the presentation is using a stop switch mechanism to be able to shut down the wind turbine. And many of the ones that come with their own control mechanisms also have built-in stop switches. And typically what the stop switches do is they disconnect the turbine from the battery and they essentially short out the turbine windings. So since the turbine is shorted, it then has pretty much an infinite load, and that will slow it down. And that may be a good idea if you have freezing rain coming down or large hail or something like that. You may want to do that. Yeah.
All right, and just a real quick note, because I've gotten a couple questions about the NABCEP credit, and unfortunately at this time this presentation is not certified or registered for NABCEP credits. I talked to NABCEP and they're redoing their wind program, and so hopefully next year this will be ready to be certified, but at the moment they didn't want to include much wind in their current program, so I really apologize for that. And Brian, our next question. Assuming no ground obstructions, what is the minimum tower height to get away with from the drag of the turbulence?
Wow, okay, assuming that you were in flat ground and even the grass was cut and there was like no obstruction, well, that's hard to say. I certainly wouldn't be less than 20 feet. Really the rule of thumb is at 30 feet. Primus does make a 27-foot tower. That's probably the lowest I would ever go, and that's pretty low. So, really, the thing is, over level, unobstructed ground, you're still going to get more wind speed and more power produced at a higher altitude. So, yeah, I guess I should say 27 feet, because since that's the shortest tower I know of that's available out there. But higher is better if you can do that.
All right, and our next question, how do you stabilize the wild AC, V, and frequency?
Well, when you rectify it to DC and connect it to a battery, essentially the battery becomes kind of like an anchor. So if you, for instance, have a 48-volt battery, and it might be sitting at 50 or 52 volts, as soon as the whole system connects to that through the rectifier, essentially everything's going to be operating at that voltage. Now, of course, as the battery charges, the voltage is going to increase some, but the battery will essentially provide that kind of stabilization force to stabilize the voltage at that voltage there. So the frequency is not going to make a difference, because when you run AC rectifier, current, no frequency issue. So it's just inherent in the system that it's going to operate at the voltage of the battery, since everything is connected essentially by wiring through there. There may be control devices in the middle, but essentially it's all passing through and is really connected to the battery. So a 24-volt battery is going to run at 24 to 28 volts, and a 48-volt system is going to run at 48 volts to 58, 59 volts or something like that, depending on the state of charge of the battery. And so the short answer is that the battery provides a stabilization for the system.
Great, thanks, Brian. The next question we have, can you offer an opinion on mechanical furling versus electrical braking?
Okay. Well, most of the small turbines just use electrical braking, because mechanical furling is a more complex issue. But it is really a better way to control wind regimen. On large wind turbines, for those who don't know, mechanical furling is there's actually two ways to do it. One is to actually change the relationship of the blade to the wind by essentially spinning the blade in or out of the wind. Another is to move the whole turbine out of the wind, to move it sideways to some extent, and therefore move it out of the wind path, or reduce the face to the wind path, and thereby reducing the amount of energy that the turbine can produce. So both of those methods work really well. I mean, the older Whisper wind turbines had a furling device where it was essentially half the housing was spring-loaded and was at an angle, so as the wind blew really hard, it just pushed against that spring and would actually pull the turbine blades out of the path of the wind slightly and equalize to the wind speed. Excellent way of doing it. Helps protect the wind turbine from overspeeding in real high wind applications. It's just, there are more moving parts in that situation. So it's a trade-off between moving parts and service issues and just having electrical braking, which is either directly shorting out the turbine or even doing a partial loading on the turbine, similar to where the Midnight Clipper would do, where it just loads the heating elements based on the amount of power produced. So it's just two different ways of controlling the turbine. The big wind turbines use a variety and usually a combination of those methods to control their output and protect the turbine during high wind situations. I think that that might be a good question for some of the turbine engineers as to what they think. I just think that it's just tools in the toolbox in the sense that turbine manufacturers use depending on the size of the turbine and the budget that they have for the project and whatnot, as to choose what kind of furling there is. But certainly, mechanical furling is an excellent way of controlling a turbine, and is typically used on turbines that are 5,000 watts. Control with electrical means. So the electronic braking is really used more in smaller turbines than big ones, but I think that the real big ones use a combination of the two. That was a good question.
Thanks, Brian. Our next question, can you address briefly your experience with AC coupled systems, specifically marrying solar with SMA inverter, batteries, SMA Sunny Island with backup generator on site too? Is adding a small turbine to this mix easily done?
Well, actually, with the SMA system, it is fairly easily done. SMA also makes minor inverters called the Windy Boys, and essentially they're Sunny Boy inverters that are just tweaked in a way with the maximum power point tracking and whatnot to operate with a turbine rather than a PV array. And since it's all AC coupled, it doesn't really matter to the power system, where that energy is coming from. Whatever the DC voltage is, it's for DC on the side. So, SMA has done a lot of work in that area. They've pretty much pulled out of that market, at least in the U.S., and probably internationally, again, because of the lower price of PV. There's such little demand for it that it's just not worth the manufacturer's trouble to really support that kind of system. But they're certainly out there, and some of the medium-sized wind turbines, or small to medium-sized, for instance, Berge Wind Power, which is one of the really fine manufacturers in the U.S., they make a 10 kilowatt unit that's designed for direct grid tie. It has its own grid tie inverter, and it could just be mounted and installed as just another grid tie inverter in parallel with PV inverters. So there's really no issue there. I mean, you could have Sunny Boy or some other brand of grid tie inverters on your PV arrays. You can have a Berge, what they call the XL10, and they're 10 kilowatt design of grid tie inverter, and it just mounts in parallel with the solar inverters and produces energy that goes onto the grid. And obviously, that could even be done off-grid in an AC coupled system. It could be done in microgrids or mini grids. There's a number of ways to do that. So yeah, I mean, if you're just working with DC to AC inverters and mostly grid tie inverters, there's really not much difference between a grid tie inverter for wind and a grid tie inverter for PV in terms of its actual functioning. Obviously the internal electronics and the programming are different, but in terms of hooking them up, it's pretty much the same thing. You just parallel it along with your PV inverters, whether it's on the grid or in a microgrid.
Great. The next question we have, Brian, do you have any experience with Pico wind or higher voltage wind turbines to charge higher voltage batteries?
I don't have I've seen turbines mostly out of China running at 300 or 400 volts DC. I'm not sure how the application fits in terms of the rest of the infrastructure of the systems. It could certainly be done. I think we're going to be seeing a lot more high voltage DC battery systems in the future. I think Tesla has certainly broken the ice on that one with their Powerwall unit, which operates in the roughly 350 to 400 volt DC range. I see no reason why wind turbines or PV inverters or anything else couldn't also operate at those higher voltages. I'm not seeing a whole lot of products on the market yet, and I'm not sure how the National Electrical Code is going to handle the high voltage batteries in residential applications. Now there's a restriction to 48 volts, which is pretty much why we're there. High voltage battery banks are a whole lot more dangerous. So until we get into, lithium ion technology and whatnot, so you're going to have, a flooded L16 battery wired up at 300 volts with lead terminals. That's not going to be safe. So until we start seeing the infrastructure and the parts and the components for doing higher voltage DC battery banks, I don't think we're going to see a lot of that. But we may see it in the next few years. And obviously, situations like that have been available for industrial uses and utility uses. Many utility companies use large wind turbines. It's all very high voltage. It's connecting to medium voltage grids very often at 17,000 volts or higher. Yeah, I mean, this can certainly be done. Obviously, if the power from the wind turbine increases, there's big advantage to going up in voltage because you're handling less amperage at that point. Your wiring can be smaller, your efficiencies are much greater, you can run much longer distances with higher voltages. So yeah, I don't have any direct experience with that, but I have done some high voltage electric plants. Also put a wire free phase, and you can bump that up in voltage and send that long distance through really small wire. I have done one or two projects like that, but I haven't done that with turbines. But it could certainly be done. It's just there isn't a lot of equipment out for the residential or small commercial market that really make that possible yet. Well, we may see that more.
All right, and we'll do our last question here. Brian, you mentioned earlier that there was a major manufacturer coming out with a new small wind turbine. Can you reveal who that is?
Well, right now it's more in rumor, although I did hear it from somebody fairly high up in this company. I'm going to let them announce that. I understand it's going to happen at Solar Power International in Las Vegas next month. I don't know if that's actually going to happen. I don't want to spill the beans on them, though. But right. I do find it interesting that there is another that's looking at wind. That's a wonderful thing.
All right. Well, thanks so much, Brian, for answering those questions, and thank you to everyone who submitted questions. We got a lot of really good ones this time. And that concludes the Q&A portion of our webinar. Thanks, everyone, for joining us for our presentation of off-grid wind power. And just a quick note, next month, our next webinar is September 23rd, and the topic will be off-grid system design. So another really good one to mark your calendar for. And just also another reminder, we will put these on our YouTube channel. So if you missed part of it or want someone else to see it, go ahead and check out our channel. It's just called AEE Solar, and we have all of our past webinars up there. And we'll continue to put those up as we present them. So thanks again, Brian.
Well, thank you, Hannah, and thanks everyone who attended. And I don't know if you can still see the screen, but that's a slightly larger wind turbine. I figured I'd put that in there at the end.
All right. Well, thanks again, everyone, and have a great weekend.